Okay, with that settled, the Oscar's third lecture. Okay, so in this lecture, the next one, I want to talk about an application of what I talked about in the last two lectures. So it's going to start sounding quite different, and these things will show up near the end. So the application is to spaces of Riemannian metrics of positive scalar curvature. And you might be a bit surprised, as I was, that you can apply the ideas in the first two lectures to this question. I want to explain in this lecture the statement of the theorem that we can prove in this direction. And I want to explain some of the background to it and some of the tools that are not ours that go into it. Ours, incidentally, for this is Boris Botvinnik and Johannes Evert, who, if you don't know who that is, that's what I ask all the questions all the time. So first I want to explain what positive scalar curvature is. 18 months ago I didn't know what this was. I've never studied differential geometry in my life, disgracefully. So I'm going to give you the sort of intuitive, but when it comes to calculation, it's not terribly useful definition. So for a Riemannian manifold, M manifold G is the Riemannian metric. The point P or X in the manifold, the scalar curvature at X one can define this in the following way. You can look at a ball of radius E centered at the point X, and radius here means, geodesic radius with respect to this metric, and you can compare that, I suppose I better fix a dimension, D. You can compare that, or rather you can compare its volume with the volume of the standard ball with radius epsilon centered at, say, 0 in Euclidean space. And you can ask how close those are. And epsilon, of course, means some small number, and we're only going to ask this for small enough balls, and so you can sort of expand it. You can find a Taylor expansion in terms of epsilon, and you can ask what it looks like, and to first order they're about the same, or to 0th order they're about the same. Turns out that to first order they're also about the same, but to second order there's a difference, and the difference is more or less the scalar curvature at that point, except that there's some normalizing factor, 6t plus 2. So you can see, of course, that this is not the first definition, because you wouldn't put all this rubbish in if you were going to define it this way. Plus 5 things. And so S of X is the scalar curvature at the point X. So S defines a function, and the manifold, at each point picks out a scalar curvature. And the point of this being positive, the scalar curvature at X is positive. What does that mean? It means the ball is a little smaller than the Euclidean ball. Okay? Which is precisely the sort of thing that a ball on the round sphere, for example, the upper hemisphere has. It's slightly smaller, in fact, if you take the whole upper hemisphere, it's quite a bit smaller. But any ball you take on a round sphere is has a little bit less area than the Euclidean ball of that radius. So if it's positive, then balls are smaller than Euclidean balls. So it's completely not obvious that a manifold has, say, a metric that has positive scalar curvature, and in fact, some don't, and we'll come to that a bit later. But I want to suppose for now that I'm only going to be interested in manifolds that do have one, because I'm going to study the space of all of them. And if it doesn't have one, then that's not such an interesting space. So let me just say a couple of careful things first. So if M has boundary, boundary of M, and a collar C. Then I'm if I'm talking about Riemannian metrics of any type on M, I'm always going to insist that on this collar they're a product metric. Okay? So then I insist that if I pull back G, where G is any metric I ever might mean, I get dt squared, where T is this coordinate, plus whatever G is restricted to the boundary. Okay? So I'm not going to allow things that behave funny in the boundary, because they just look straight. Okay, and as a point of notation, I'll let R of M be the space of all Riemannian metrics on M. And I'll write R plus for the subspace of ones which have positive scalar curvature at every point. Subspace. Those with positive scalar curvature. Okay, so that's my definition. So remember, if M has boundary, all my metrics have to be a product of the boundary. That goes without saying, always. So these necessarily are as well. And again, this space might be empty. And one last thing, so if I fix a metric, a positive scalar curvature metric, on the boundary of M, I let R plus of M subscript H be those which on the boundary restrict to H. So it's a matrix such that G is restricted to the boundary of M equals H.
Since you're setting this up so carefully, is it that there should exist a collar on which this is, or do you fix the collar?
Fix the collar. Manifolds have given collars all the time. There's a little bit of freedom. You might not ask for that on the whole collar. Maybe you just want it eventually. Okay. All right. So now I want to remind you about some index theoretic things, which I know very little about, but thankfully Thomas Chick has given some fantastic lectures and explained all of the difficult parts. So I'm going to explain some trivialities in this direction. So remember, spin D is the double cover of SOD, and one can construct it as certain units in the so-called Clifford algebra. It can be constructed as a group of units in the Clifford algebra, which is by definition the following thing. I take the tensor algebra on the vector space Rd. So I take all the words in vectors of Rd, and then I divide out by the following. Whenever I have the symbol vector tensor vector, I set it equal to minus the norm of the vector times the unit. Squared. 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 Okay, so this is some algebra. I divide out by this ideal, I get an algebra, and this contains, in a standard way, just as the vectors, the monomials of length 1. And because I've asserted that the group spin is a certain group of units in here, I don't want to go into exactly how it is, it acts as the Clifford algebra on either side. So, that's one point. If I just have a smooth manifold, the tangent bundle Tm has structure group, the general immediate group. all you know about it. If I pick two pieces of data, so choosing one annotation, okay, and two, this is not very good. First an orientation and two of a main metric. I get a reduction of the structure group it's group 2 SOD. Okay? And SOD is the thing of which spin D is the double column. So, the spin structure on M, the metric, is a principal spin D bundle, which I call D spin over M, and an isomorphism of the underlying SON, SOD bundle with the standard one. So I take the spin 1, I cross it with spin D with SOD, and I ask for a choice of identification of that with the principal SO bundle, the manifold has coming through the orientation and the metric. So this is part of the data. Right. If I have such a thing, so given a spin structure, I can form S dollar of M is the following vector bundle. I take the principal spin bundle, the start of the data, and I cross it over spin D with the Clifford algebra, where this group acts here by left multiplication because it consists of a load of units in this algebra, so you can just multiply on the left. So what properties does this have? This is the vector bundle. But because the Clifford algebra was an algebra, I can still multiply on the right by elements of the Clifford algebra. So it still has a residual action on the other side. A vector bundle, or let's say a bundle of right. Right. Now, so that's one thing that having a metric buys you. You have this compact structure group SOD around, and you can talk about spin D lying over it. Another thing that it buys you is that you have a notion of covariant derivatives, and so you can write down the following thing. I can look at the space of smooth sections of my bundle, the spinner bundle, and I can look at covariant differentiation, which gives me a smooth section of the cotangent bundle tensor. Then I can use the metric to identify the cotangent bundle with the tangent bundle. Okay. And finally, I can use the fact that what have I done on each fibre here? The fibres here are just identified with RD. The fibres here are identified with the Clifford algebra. And RD sits inside the Clifford algebra, and so I have a multiplication. It's just a fibre-wise version of this being inside the algebra and acting. So I can just multiply, I can just act. And I can get a section of the bundle again. And this whole composition is the Dirac operator associated to the metric G. So let me just write down what basic properties this has, and it has properties that Thomas has been talking about in his last few lectures that will be quite familiar to you. So this has, firstly, it's a degree 1 differential operator. operator which is elliptic and formally self-adjoint. So that's the operator part. Just as a matter of linear algebra, it's sections of a bundle that had this extra Clifford multiplication defined on it. And so it also has a pointwise Clifford multiplication defined on it. And so it is CLV linear with respect to this multiplication on this space. So if you have a section, you can just pointwise multiply by the Clifford algebra. And there's one final thing, which is that it is rated rather, which I don't want to go into, but which is very important. What that means is that both sides have natural involutions, and it swaps the two eigenspaces for that involution. And how is this related to the things I was saying about scalar curvature before? Well, it's the following theorem, which has sort of, I'm not sure who exactly is the correct person to attribute this to. I think perhaps Thomas Selby Schrödinger, in fact, was the first person to prove this, but nobody knew about it. So what it says is the following: if G is positive scalar curvature metric, then this operator is invertible. And that's the relation, or that's rather why index theory is such a fantastic tool for studying positive scalar curvature, is because, well, in particular, if it's invertible, then its index is 0. Right? But on the other hand, its index doesn't actually depend on the metric. The index is a topological invariant. So if it has a positive scalar curvature metric, then the index of this has to be 0, but then so does the index of any other metric. In particular, if you can find some metric for which the index is not 0, then there cannot exist any positive scalar curvature metric on that manifold. And this index, incidentally, is basically the A hat genus. So you just take any manifold with non-zero A hat genus, and that can't have a positive scalar curvature metric. But again, I don't really want to talk about the existence or non-existence question. I want to suppose they exist on some manifold and look at the space of all of them. So what does this theorem buy us on the space level? Well, one can set up the following interesting commutative square. You can start by looking at the space of Riemannian metrics on the manifold M. And each Riemannian metric has a Dirac operator. So we've fixed the spin structure, which we now don't talk about anymore. Okay? So each Riemannian metric has a Dirac operator, and so you get a function from the space of metrics to the space of things which the Dirac operator is. Okay? And what is that space? Well, there's a little, whatever goes here in a second. It's Fred D, it's the space of Clifford D linear Fredholm operators that are self-adjoint and graded. But for the purposes of algebraic topologists like me, it's a model for the deep loop space of Z cross PO, i.e. it's a space that represents minus D real theory. So this is a Singer. And there's one small issue here, which is that the Dirac operator, being a differential operator, is not a bounded operator. And so you have to do this functional calculus that Thomas has been describing in order to get a bounded operator, and I can just write that in symbols as I'm applying the function x over square root of 1 plus x squared, which is an odd function, to the operator dg in the sense of functional calculus. So that's now a bounded operator as it represents an actual point in this space. Okay, so up inside here, we have the space of positive scalar curvature metrics. And what does the theorem say? It says if we start here, we don't get any old operator, we get an invertible operator. And so we land in the subspace of invertible operators. This is the fundamental square in this subject, because what do we know about the space of all Riemannian metrics? Well, it's contractible, right? You can just linearly interpolate between the two Riemannian metrics. On the other hand, what do we know about the space of invertible operators? Well, that's also contractible, though for a much more difficult reason, like the theorem of Kuipert. So these are both contractible. And consequently, the map from there to there is not very interesting. But it is very interesting because it's contractible twice. The map from there to there is null homotopic for two separate reasons. Firstly, it's null homotopic because it factors through all metrics. And secondly, it's null homotopic because it factors through invertible operators. And so by choosing a contraction of these two spaces, we get a map from this space to the loops on that space. There's a small technical point here, which is that what does it mean to choose a null homotopy? It means you choose a homotopy to the constant map at the base point. Okay? Now this space contains the base point of that, so you can just contract it to its base point. This space is contractible, but you still have to choose a path to the base point. So the easiest way to do that is just pick a point in this space. Then you can contract that to that point, and then you're in the invertible operators and you have more or less canonical. Okay? So choosing a base point metric R plus M, you get a map that's called the index difference based at G0 from R plus of M to loops on the space of Fredholm operators that are typically linear, and that's a model of the space loops D plus 1, D equals B. And we want to use this map in order to try to detect non-trivial equality in this space. Right? If you just had some loop in this space, well, how on earth do you know if it's non-homotopic or not? But if you can show it's not non-homotopic over here, where you know what pi 1 is, then you've won. And this idea, this strategy for detecting non-triviality is not ours, it's due to Nigel Hitchin. And he used it to show that the space can be disconnected.
Thomas Larsen as well.
I think Hitchin earlier.
Yeah.
So this even makes sense on pi 0, right? This space is disconnected. If you can find 2 points in here that go to different points over there, well, you've shown this space is disconnected. And that's precisely what Hitchin did. But it's quite difficult, even if you pick a nice manifold like a sphere or something. So there's one obvious point in here, I hope you agree, which is that metric on the sphere. And then you've got to produce another one. You've got to produce another one. I mean, you can do obvious things, wiggle it a bit. It's sort of obvious that that's on the topic of the one you started with, because that's how you built it. So you've got to construct a new one in some way that's not, at least one criterion is it's not obviously in the same path component as the round one. And this is where diffeomorphism groups come in. Because if I've got a metric and I have a diffeomorphism, I can pull the metric back along the diffeomorphism. And if the diffeomorphism is not isotopic to the identity, then there's no reason why that metric ought to be isotopic to the one you started with. So the construction that Hitchin gave is as follows. So you let phi, it doesn't even need to be a single diffeomorphism. You can even start with a homotopy class in a space of diffeomorphisms of, let me do a sphere for now. Suppose I've got an element of pi k of the diffeomorphism group with a sphere based at the identity. And then you can form the following. You can go from the sphere to the diffie-Morton group using phi k. You can act using the diffie-Morton group on the base point metric that you've chosen, and that gets you into here. And then you can apply the index difference construction, and that gets you into loops n plus 1 equals BO. And you can ask, okay, we know what pi k of this group is. How do I describe this element in terms of the things I started with? So this is the index difference now. And it's important here that we use the same metrics on both sides. That's what I have to say. And the little geometric lemma that improves is that this class, x is this class, the class of x in ko minus e plus 1 of a point is the alpha invariant, and I'll say what this is in a second, of the Sn bundle over Sk plus 1 that you get by gluing together two trivial Sn bundles over k plus 1 disks along the boundary. So that's the clutching construction. So I mean alpha-vertical space. Okay? In particular, it doesn't depend on G0, and that's because we use the same G0 here, they sort of cancel out. So what are these things? So one, what is alpha? Alpha is the map in the cobordism group of spin manifolds to K groups, K to a point. And it's the map basically that sends M to the index of a Dirac equation with respect to some metric, and it doesn't matter which because it's a topological invariant. If you're more homotopy theory flavored, it's also the map you get on homotopy groups by the Taylor-Bott-Shapiro orientation of spin cobordism. So that's what that is. And the second point is that suppose we take now k to be 0, so we're just doing pi 0, we're trying to detect disconnectedness of this space, then, so for k is 0, what is this E n plus 1 phi? So you have, it's a mapping tools, right? And you can do surgery on one fiber, and you'll see that what you get there is a homotopy sphere, and it's the homotopy sphere you get by clutching on phi. So this is not equal to the homotopy sphere you get by clutching along phi in the notation from Demmer's talk, but they're coordinate. Okay? And then it's well known that there exist homotopy spheres that have non-trivial alpha invariant. So there exist ones in dimensions 1 or 2 or 8. With alpha sigma not 0, and that shows that in dimension 0 or 1 mod 8, the space of positive scalar cogeometrics on the sphere is disconnected. That's Hitchin's argument. And what I want to talk about is sort of that was on pi 0 we did this. You could also do a similar thing on pi k. But homotopy groups and diffie-Morton groups are rather difficult. And the theorem that I was talking about in the last 2 lectures was not about homotopy, it was about homology. It wasn't about homology of diffie-Morton groups, it was about homology of classifying spaces of diffie-Morton groups. And I want to explain how one can use those techniques instead. But this is the motivating idea. Okay. So now I want to explain what I think is a truly remarkable theorem. Reading about this is what got me interested in this whole subject to begin with, because as I said, this is not my background, isn't in this sort of area. And it's about I've got a positive scalar curvature metric on a manifold, and I change the manifold by surgery, what can I say about whether or not the new manifold has positive scalar curvature? So I'm going to set it up like this. So suppose I've got inside my manifold dimension D, suppose I have a submanifold with trivial normal one. So the submanifold trivial normal one. Trivialized normal one. And then I want to describe a metric, a particular choice of metric that I make once and for all on the disk. Okay? And it's called a torpedo metric. On the disk is, and let me just draw it first, and then you'll see why it's called what it is. So that is abstractly a disk. But the metric is such that near the boundary it just looks like this sphere cross interval. And near the middle it looks like a hemisphere with a disk. Okay? And in my picture you might get a bit worried because this stuff out here, that's a circle across an interval. And its curvature is 0. Right? Circle has curvature 0 and the interval has curvature 0. And so it's indeed true that if d minus k minus 1 is too small, then this will be no good. But if d minus k minus 1 is at least true, then you can find a metric of this that has positive scalar curvature. Okay? So the properties are that near the boundary it looks like a cylinder, and near the middle it looks like the metric on the hemisphere. Okay? And you can't literally glue the metric on the hemisphere and the metric on the boundary together, because they don't fit together smoothly, but you can wiggle them a bit so that they do. Okay, so that's what a torpedo metric is, and I'll call it G tau or something. Of whatever dimension it is. And now you can do the following thing. So fix positive scalar curvature metric on N with some manifold. And let R plus of M comma N cross D minus K semicolon G. Call that something else. Gn. Gn. So this is a subspace of metrics that are just standard on this submanifold. So it would be those G such that G restricted to N cross D is just equal to the metric on N plus the metric, this torpedo metric on the disk factor. Okay, so they're just completely fixed on this standard subpart of the manifold. And then the theorem, which was proved independently by Schoenich and Walsh, and is based on an earlier result of Gorman and Lawson that I'll mention in a second. Is that if d minus k is at least 3, which is necessary for this situation to make any sense whatsoever, then the inclusion of this subspace into this space is a homotopy equivalence. And let me just give it a name. And this is, I think, a truly remarkable theorem. I mean, I could sort of believe that given some metric, you can wiggle it so that it becomes standard on this subpart. I can believe this is subjectable by 0. But the fact that the entire space of metrics are homotopy equivalent, so given any family of metrics on M, I can move it through a family of metrics on M so that it's completely standard on this submanifold, I think is astounding. And it was reading about this that first got me interested in the subject, and I thought, well, in fact, let me tell you one more thing.
I mean, don't you think the Pi naught surjectivity is least as remarkable. So if you can show finite surgibility, you make your hands dirty and have to do an atomic equivalence.
Don't I think that?
This
That's
is
the question. I think that's if you tell me to.
Yeah, no, doesn't matter.
I don't know, like I say, I have very little feeling for these things, but I think it's an amazing result. Even more so, given the very easy corollary that are now actually proved for you. So the corollary is let phi be a piece of surgery data. So I've got the framing built in into my manifold, and m prime the result. The result of doing surgery. Then if K is not too big and not too small, but just right, then the space of positive scaling curvature metrics on M is homotopy equivalent to the space of positive scaling curvature metrics on the result. And it was really this result, which I learned about first, before that one, that really convinced me that this was amazing. And the proof is trivial based on that. What do? You look at metrics on M, you look at the subspace of metrics which are standard on the surgery data. And standard means, let's take it into the actual round metric. So G round on the sphere. And now over here, you look at metrics on the surgeon manifold that are standard on its piece of dual surgery data, which is a D A plus 1 cross S D minus K minus 1, also with a round metric on this now. What do you know about these spaces? Well, I mean, they're basically equal, right? Or at least homomorphic. You've got a metric on here that's standard in this piece. So what it is in this piece carries no information, so you may as well cut it out. Similarly here, you've got a metric on there which is standard on there, so you may as well cut that out. If you cut that out of that, you get the same thing as if you cut that out of that. So let me be a bit bombastic and say they're equal. And then you have the inclusion of this into here. And under these two inequalities, meaning one of them flat to be an equivalence and one of them flat to be an equivalence, and that's it. It's amazing. And not only that, not only are they equivalent, but in fact the choice of surgery data you'll see gives you a homotopy class of homotopy equivalences.
So how does the specific range of K go up here?
Oh, so there was, it's just to verify that. And you have to verify it twice, so there's a double inequality. You can now, and this is very anachronistic, but you can now take pi 0. And in particular, it implies that if that's not empty, then that's not empty.
Pi minus 1.
And vice versa. Sorry?
That's pi minus 1.
If you like, you can take pi minus 1.
That's
Right.
a truth value.
And that follows, so it follows that the property of admitting a positive scalar curvature metric is coordinate invariant as long as you don't do too small or big dimensional proportions. And that was the thing with Gormley and Lawson, which it was sort of proved on the pi minus 1 level first.
I mean, then you can lose the one restriction.
Sorry?
Then you can lose the one dimension restriction.
Was that right?
Yes.
Yeah, because the one inclusion you don't need it to.
Oh, that's right. If you just want to go in one direction, yeah. Yeah, that's right. Okay. Now let me try to connect this with what I've been talking about earlier in the week by stating the theorem that we have in this direction. So this won't show up in the theorem. This is a tool that I'll use tomorrow to explain how we prove our theorem. So remember, the tangential structures what I call theta n, and they were, you take BO2n and you take the n connected cover. So these are the ones I talked about on Tuesday, and it has an associated Thom spectrum called MT theta n, and it also has an associated infinite loop space called loops infinity MT theta n. Okay? Now, if n is at least 2, so we've taken a 2-connected cover of BO2n, then we've made the bundle that this pulls back to here is spin, because this space is 2 connected, and so any bundle is spin. So for n at least 2, the bundle theta n star gamma d is spin. And that means that its Thom space, or spectrum, has an orientation, or has a Thom class, if you like, in real K-theory. So MT theta n has a KO Thom class, which I think I call something like alpha. MT theta n. And now you have to be careful here. So remember, the bundle this classifies as 2n dimensional, and we take the Thom spectrum of minus that one, or its orthogonal complement. So this is, so the Thom class is in degree minus 2n. Okay. And I'll just point out that if you're familiar with this sort of thing, then you know about this Atiyah-Bock-Shapiro orientation I mentioned earlier, which is the thing more often called alpha. And just by going from B spin to n to B spin gives a map like this. So it's a sort of unstable version of the usual Atiyah-Bock-Shapiro orientation. Yeah, so that's the thing they call alpha, but I'll like alpha for this one. I can state the theorem. And the theorem says that W2n be spin, 2n be 6. G naught be a base point in the space of positive scalar cogeometric, so implicitly it has to not be empty. Then there's a map. Rho from the loop space of the infinite loop space of MT theta, which I write as loops infinity plus 1 of MT theta n, to the space of positive scalar cogeometrics on zone. Such that if I compose, this depends on such that if I compose rho with this index difference map, so that now gives a map from loops infinity plus 1 of MT theta n to loops 2n plus 1 of z cross BO. Then this is homotopic to the loop map of this alpha orientation. And there's some slightly technical thing here. This means weakly homotopic, and it also means up to phantom maps. But that makes no difference to any calculation.
Is it the same? I mean, weak homotopy?
No, that's not the same.
Not the same?
So luckily, both of the luckily the target is an infinite loop space. So a phantom, and you can just take the difference of the maps, and the claim that the difference of the maps is null homotopic on any finite CW compass. But unfortunately, this is not. Right, so that's the theorem. And the purpose of this theorem is that the map alpha is defined purely using homotopy theory. And in particular, if you want to compute what the map alpha does on homotopy groups, then you know exactly where you are. You know, you have atom spectral sequences, you have homology operations, you have all the classical tools for algebraic topology. On the other hand, this theorem says that it factors through this very interesting space of positive scalar coefficient matrix on top. So for example, if you can show this is surjective on homotopy groups, then implicitly the index map is surjective, or the index difference map is surjective on homotopy groups. Admittedly, it doesn't give you a very concrete family of positive scalar coefficient matrices. Even if you do understand the proof, it's still true that it doesn't give you a very concrete description. But it does let you compute all sorts of things. And in the last few minutes, I'd just like to explain the most basic calculation you can do with this. Oh, I just say the words. There's also a version for odd dimensional manifolds. But it still uses the same spectra. So it's still the 2n, but that also works for odd dimensional manifolds in dimension 2n plus 1. I will get to that. So corollary is that for WD spin D at least 6, the map from homotopy groups, kth homotopy of R plus of n of n, based at some base point, to pi d plus 1 plus k, which is how this shift works. Or rather, a better thing to say is 2 ko d plus 1 plus k, which you'll remember is either z mod 2 or 0. It's z if d plus 1 plus k is congruent to 0 mod 4, and it's z mod 2 if the same thing is congruent to 1 mod 2 mod 8, and it's 0 otherwise. So the corollary says that in this situation, this map, which is the one index given by the index difference, is non-zero whenever the target group is non-zero. So in particular, that means it hits all the z mod 2s, because that's all you can do with group of order 2, and it hits a non-trivial subgroup of all the z's. I'll just point out that, maybe I'll say it, so there were early results in this direction about, so as I said, the pi 0 result was worked out by Hitchin in this thesis. There is a result of Thomas Schick, Bernard Hanke, and Wolfgang Steiner about higher homotopy groups and detecting them using this map. They knew about that some of this stuff was hit, but their results have a range, so the dimension of the manifold has a range, so you only know this up to some range. And there are also results of Dermot Crowley and Thomas Schick as well, that they knew some of the Z mod 2s that hit, I think. That's right. But it follows from this stable homotopy calculation, if you like, that all the Z mod 2s are hit, and all the Z's are hit as well.
I think we hit all the Z's.
Oh, did you? Okay. So let me explain the proof of this, which is now just a little quantum theory calculation. So the first part is that, given that, okay, how are we going to prove it? Well, we're going to use the main theorem. Right? So what we're actually going to prove is that when you precompose with this map rho, or rather we're really going to prove that the map alpha has this property. Okay? So we need to show has this property. At least the theorem will prove that for even d, and then I asserted that for odd d this is a similar thing that I'm writing down, so let me just explain that. So the proof in the Z02 part is as follows. This is a Thom spectrum, so it has a sort of lowest cell, which is the cell that carries the Thom class. Which gives you a map of spectra from the -2n sphere to this Thom spectrum. And then you can compose that the map alpha, and you get into KO, and you wonder what this could possibly be, and of course it's the only thing it could possibly be, it's the unit for the ring KO that is suspended to activities. And then you look at the work of Adams, and he just immediately shows that the unit hits all the Z-vectors. So that proves half of it. So the unit from stable homotopy to KO hits all Z-vectors. So in fact, this much simpler spectrum would do already to hit all the Z-vectors, which is quite remarkable. That's the easiest part. And for the second part, I want to show that a map to a Z is non-zero, so I may as well rationalize. So for the Z's, can show that homotopy. You can show that the homotopy groups of M, T, theta, N, rationalized, going into KO. Shifted, rationalized. This is the thing I need to study. But of course, rational stable homotopy theory is rather easy because it's just rational homology theory. So this is just rational homology of MT theta n. And MT theta n is a Thom spectrum, so you have a Thom isomorphism. So this is just rational homology of this n-connected cover. There's some shift here that I haven't kept track of. There's some shift of degrees, maybe. And if I fix some degree that's I got this right. Will be plus 2 as well then, yeah. So in degree where star plus 2n equals 4k, this is a map from rational homology to Q, i.e. it's a cohomology class, and which cohomology class is it? Well, it's the A hat genes. This map is A hat K. So all you need to know is that on this connected cover of BO2N, the A hat genus is still not 0. And that's very easy because in fact this leading term, the indecomposable part is already not 0. And that's it. So we just reduce this to just stable homotopy theory calculations. So this is the easiest possible homotopy theory calculation. There's one more that I want to tell you just because I find it amusing. You can also show, using much more serious homotopy theory, in particular using the work of Mazin and Schichter on the cyclotomic trace and things related to that, you can also show, or you can look at the map. Let me just do the case 2n equals 6. And then the map we're interested in goes from pi. I want to land invert 2. One can do certain calculations with this spectrum. You get the spectrum dimension 6, the spectrum called MT spin 6. And you can relate that to the spectrums MT spin 2 and MT spin 4, which are, that's just pure homotopy theory. That the theorem, the main theorem, doesn't say anything about manifolds of dimension 2 or 4. But once you've got these spectra around, you can use things that the theorem doesn't apply to study them. And Madsen and Trickle studied this spectrum MT spin 2 or MTSO2, but when you invert 2, those become the same. And they studied its homotopy, and they studied the infinite loop space, and they found certain very fancy splittings of this, as splittings as spaces, but not as infinite loop spaces and stuff like that. And the upshot is that you can get a number theoretic description of the index of the image of this map in terms of numerators of Bernoulli numbers. And then you can track that number theoretic description. And one consequence is that this is onto the degrees less than 4,000 by doing this number theoretic calculation clearly on a computer. And it shows that the number theoretic formula that computes the bound, at least on the index of this, is 1 in the first 4,000 cases. And in principle, that's a conjecture that one could give to a number theorist, and they could try to prove or disprove. It would only be a bound, so really the theorem is about the image of that map. But of course, if the long map's subjective, so is the short one. Yeah, so that's quite fun, I thought. Of course, it also hits all the Z12s, so I could have just done that. Yeah, just don't worry about this.
It's only been checked in these cases?
Yeah, so I mean, this would just be putting it in the label.
I mean, you have to invert 2.
No, you hit all the Z12s already.
You could also.
No, sorry, you're absolutely right. You're absolutely right. Sorry. You might only hit it 2 to the k times of error, so you have to invert 2. You're absolutely right. Okay, let me stop there.